In this class, I will explain another problem on Orifice and also I will discuss the derivation of discharge equation of a rectangular mesh. So this problem, Orifice problem states like this. The head of water over an orifice of diameter 10 cm is 10 meters. So diameter of the orifice is 10 cm, that is 0.1 meter, and it is a circular orifice. Head over the orifice is 10 meters. This is the diagram. So this orifice is this opening, and head is measured from the center of the orifice up to the free surface. This is 10 meters he has given. Water coming out from the orifice is collected in a circular tank of diameter 1.5 meter. See, so the jet of water emerges out of this orifice. That water is collected in a circular tank. So plan of the tank looks like this, and this is the elevation. So it is collected in a circular tank of diameter 1.5 meter, that is capital D. The rise of water level in this tank is 1 meter in 25 seconds. That means water collected in this collecting tank, circular tank, so it is measured with respect to time. In 1 meter rise of water, 1 meter rise in water has taken 25 seconds. So in 25 seconds, there is a rise of 1 meter of water. The coordinates of the point on the jet measured from Vina Contracta are 4.3 meters horizontal and 0.5 meter vertical. So this is the Vina Contracta portion. X is the Vina Contracta, where the area of the jet is minimum and velocity is maximum. From that, a point in the jet is taken. P is the point. So the horizontal distance of P is 4.3 meter from X, and vertical distance is 0.5 meter. Of course, it is downwards. From this data, we have to calculate the hydraulic coefficient CD, CC, CV of the orifice. This is similar to the last problem which I had explained in the earlier video. So here, only difference is, instead of giving the actual discharge directly, he has given the tank dimension and the time taken for a certain rise in the water level in the tank. So that means you have to compute the actual discharge. In the last problem, actual discharge was directly given. Here we have to compute the actual discharge. Now, the data, let us write the data. So H has given 10 meters constant head over the orifice. Diameter of the orifice 10 cm is 0.1 meter. You can find out the area of the orifice A0 pi d square by 4, which comes out to be 7.8 to 10 power minus 3 meters square. Everything should be in meters and seconds. Now x and y, point P, for point P on the jet, the coordinates x and y, they are given as 4.3 meter and 0.5 meter. Now to find the actual discharge, so that is the question now. We have to find the actual discharge first. So actual discharge is nothing but the quantity of water collected in 1 second. So volume of water, we can say quantity means volume of water. So to get the volume, we have to multiply the area of the tank, collecting tank, by the rise of water level. So here the rise is given as 1 meter. 1 meter is the rise, and area of the tank is pi d square by 4. So now volume of water collected in 25 seconds he has given. Pi d square by 4 is the area, multiplied by rise in water level is 1 meter. So it comes out to be pi d square by 4 meter cube, becomes meter cube. Because it's 1 meter, it becomes same meter cube. Now the discharge is computed as volume divided by time. That is the quantity of water collected per unit time. So volume is pi d square by 4 divided by time is 25 seconds. So substitute the value of capital D as 1.5 meter for the collecting tank. So you get pi into 1.5 square by 4 into 25. So if you simplify this, you will get 0.0707 meter cube per second as the actual discharge. So this is the actual discharge. Now to get the CD value, coefficient of discharge value, it is the ratio of actual discharge to theoretical discharge. So I need the value of theoretical discharge also. So Q theoretical. So this is theoretical discharge without losses. So here theoretical discharge, as you know, it is given by the product of area of orifice multiplied by the theoretical velocity. So theoretical velocity we have derived that it is root dH. So substitute the values. A naught is, that is area of the orifice is 7.85 10 power minus 3 meter square into root 2 G into H is 10 meters. So if you simplify that, you will get 0.11 meter cube per second. So always note that actual discharge is less than theoretical discharge, because in actual discharge losses will be there, in theoretical discharge no losses. So now you can find out the values of the hydraulic coefficients by using the respective formulae. CD is Q actual divided by Q theoretical. Q actual is 0.0707, Q theoretical is 0.11. So take the ratio of 0.643. So this is the value of CD. Next CV, x divided by 2 root yh. So CD depends on the coordinates of the point under consideration. So x is 4.3, y is 0.5, h is 10 meters. Substitute and simplify, you get 0.962. Then CC, coefficient of contraction, CD divided by CB. So CD is 0.643, CB is 0.962, divided you get 0.668. So these are the values of the hydraulic coefficients of the given orifice. So in this problem, the difference between the last problem and this problem is that in the last problem, actual discharge was directly given, whereas here we had to compute the actual discharge by multiplying the area of the tank, connecting tank, by the depth of water, then divided by the time taken. Suppose if it is a rectangular tank, here he has given circular tank. If it is a rectangular tank, then he will give the length and width or dimensions of the tank. So multiply that, you will get the area of the tank. Multiplied by the rise in water level, you will get the volume. Divided by time, you will get the discharge. That's all. So it now depends on the shape of the connecting tank. Now coming to the notches. So you know that the notch is a device used to measure flow in channels, notches and VS. So here, discharge between the different types of notches will be there based on the shape, rectangular notch, triangular notch, if you have trapezoidal notch, Cipolliti notch, etc. etc. Now we will let us see how the discharge equation can be derived in the case of a rectangular notch. So this is a rectangular notch. Normally it is connected to, it is fitted in channels. In field, it will be made of concrete or masonry, whereas in laboratory it is made of plates, thin plates. So here, to understand the discharge equation, to derive the discharge equation, so this is the rectangular notch with width or length. You can call it as either length or width of the notch as L. And capital H is the head over the notch. Please note that here the depth of water above the seal. So this bottommost edge of the notch is called as this seal of the notch, SILL. So H is the overall depth of water, that is called as the head over the notch. Now to derive the expression for the discharge through this rectangular notch, we have to consider an elemental strip something like this. Elemental strip of this area of thickness dH at a depth h from the free surface. So here dA is the elemental area. So consider an elemental strip of area dA at a depth h from the free surface of water. That's what I have taken in the diagram. So dA is now elemental area dA will be L into this dH. So L into dH. That is your dA. Now elemental discharge you can write it as, we know that discharge is equal to Q is equal to A into V, continuity equation. So elemental discharge through the strip of area dA. Now area is only dA area. dA is the elemental area. dA multiplied by theoretical distance, because I am going to assume no losses. In all the derivations we are assuming no losses means we are getting the theoretical discharge value. So dA into VT, V theoretical. So dA is L into dH. We know that theoretical discharge is given by root 2 GH that we have used even in the case of Orifice also. So whatever depth of water is there above this strip, that is small h. So you have to take that root 2 GH as the over this area, that much flow is occurring. So flow always occurs into the head. So head above that particular area under consideration. So root of 2 GH, small h we are going to take. So if you simplify this, root 2g you can take it outside because it is constant. L into root 2g into root h dh. Now this is for the elemental discharge dq. If you want this is dq. If you want the total discharge over the entire area, then we have to integrate this. So the variable is small h here. Small h can vary from, so h is measured from here. Please note that h is measured from here. So at here h is equal to 0, whereas at here h is equal to capital H. So h can vary from 0 to capital H. That is the limit of integration. So L into root 2g is a constant. You can take it outside. Into integration of root h dh will be h to the power of 3 by 2 by 3 by 2. So we have to substitute the upper and lower limits as 0 and h. So if you do that, so you will be getting q theoretical expression as 2 by 3. This 3 by 2, the denominator becomes 2 by 3. L root 2g into h to the power of 3 by 2. Lower limit becoming 0. Therefore, only one term will be there, h to the power of 3 by 2. Now this is without considering losses. Therefore, it is called as a theoretical discharge. This is the expression for theoretical discharge. If you consider the losses, then you will get the actual discharge. So we know that earlier also I have defined actual discharge is obtained by multiplying theoretical discharge by the coefficient of discharge. So considering losses, we are going to get the actual discharge QA CD into QT. So where CD is the coefficient of discharge. So if you multiply this by CD, so it becomes 2 by 3 into CD into L into root 2g into h to the power of 3 by 2. This is the final discharge equation of a rectangular notch. So you have to remember this formula, because if the problem is given, you should be in a position to substitute and simplify. So to find the discharge, we need the value of L, that is width of the notch, head over the notch, and CD value. So of course, if you in the laboratory, what we do is we are going to find the value of CD by calculating theoretical discharge using this formula, and actual discharge by measuring in a tank. So just like this problem what I explained. So actual discharge is measured in the tank, theoretical discharge is calculated using formula, then the ratio is taken, P actual divided by Q theoretical, you will get the value of CD.